When a spacecraft slams into the Martian atmosphere at 12,000 miles an hour, the heat shield glows white hot. To get a rover safely to the surface requires a sequence of automated events that must execute flawlessly. These billion-dollar machines operate on a thin wire. During descent, there is zero margin for error. A parachute deploying a microsecond too late, or a thruster firing at a slightly wrong angle, turns decades of engineering into a crater. To bridge the gap between a successful touchdown and total disaster, NASA relies on precise predictive mathematical models. Algorithms have to react to a chaotic environment faster than humanly possible. Behind the code keeping those rovers intact is a unified mathematical foundation, and much of that foundation traces back to a single mind. The architect behind some of NASA's most critical navigation systems is an outsider who taught himself the mechanics of the stars far from any major Western research center. He developed his first theories in the resource-starved mountains and alleys of Yemen. His early years were spent solving physics equations in the margins of old notebooks, often studying by candlelight because the local infrastructure couldn't provide more. That severe lack of resources forced his brain to work harder, turning a harsh environment into the intellectual fuel that shaped his approach to physics. In the heart of the ancient city of Sana'a, he replaced international laboratories with a raw appetite for books. His mind became his only research center. His teachers recognized a unique perspective in his questions, a way of looking at the horizon that suggested he already belonged to a world far beyond his immediate geography. Relocating abroad brought the harsh reality of culture shock and language barriers. He faced a persistent skepticism from those who doubted an immigrant from a conflict-torn nation could contribute to high-level science. With the odds stacked against him, he leveraged the one asset he still possessed, his scientific knowledge. He began to rebuild his career from zero. He eventually encountered a mathematical dilemma regarding erratic orbital paths for satellites, a problem that had stalled engineers using traditional navigation methods. He bypassed the traditional roadblocks by applying an unconventional mathematical framework, providing a functional solution that mapped the trajectories with total precision. When this solution reached NASA's lead engineers, it prompted a single urgent question: where did this kid come from? His outsider status allowed him to see a solution that those trained in the establishment had missed. NASA quickly put him to work developing autonomous control algorithms for the Mars landing sequence. Because Mars is too far for live piloting, his algorithms process variables in real time to make split-second parachute deployment decisions, preventing rovers from crashing. He then applied that same logic to the James Webb Space Telescope. His team's digital filtering systems mathematically strip away the cosmic static from distant light, turning blurry data into the crisp images of galaxies billions of light-years away. His code acts as a translator, turning the noise of deep space into something humans can actually understand. He eventually moved from software into physical engineering to address the weight and efficiency limits of traditional chemical rockets. He began optimizing ion propulsion engines, which rely on accelerating electrically charged particles rather than burning combustion fuel. This optimization allows deep spacecraft to travel much further while carrying a fraction of the fuel required by standard engines. By mastering both the software that guides the ships and the hardware that pushes them, he changed how NASA handles deep space travel. By providing functional alternatives to legacy math, his work has cut years out of the research cycles for deep space navigation and saved millions in mission overhead. His code remains an active, functional part of the systems NASA uses for its flagship missions. Despite his rank at the top of aerospace engineering, he credits the soil and struggles of Yemen for developing his unique mind. He views his path not as an individual win, but as a blueprint for every youth in a difficult environment trying to find a trajectory toward a larger world. This story shifts the perspective on where we expect to find the next great scientific breakthrough. It shows that the capacity to map the universe exists even in the places where there isn't electricity to read by. A lack of early resource does not define how high a person can climb. It leaves us wondering how many other minds are currently waiting for their chance to be discovered. Let me know in the comments who you want deconstructed next.